Analog MIMO capacity in millimeter wave. Sid Emir Hossein, Binding, and Mao. Abstract. In this paper, we present a new theoretical discovery that multiple input and multi-output MIMO capacity can be influenced by atmosphere molecules. In more detail, some common atmosphere molecules such as oxygen and water can absorb the radiated energy in their natural renaissance frequencies, such as 60 GHz, 20 GHz, 12 GHz, and then 18 GHz, which belong to the millimeter wave spectrum. Such a phenomenon can provide equivalent non-line of sight NLOS paths in an environment that lacks scatterers and does creatively improve the spatial multiplexing and the diversity of MIMO system. This kind of performance improvement is particularly useful for most of millimeter wave communications that heavily rely on line of sight error transmissions. To sum up, our study concludes that since the molecular eradication happens at certain millimeter wave frequency band, the MIMO capacity becomes highly frequency selective and enjoys a considerable boosting at those millimeter wave frequency band. The impact of our new discovery is significant, which fundamentally changes our understanding on the relationship between the MIMO capacity and the frequency spectrum. In particular, our results predict that several millimeter wave band can serve as valuable spectrum windows for high efficiency MIMO communications, which in turn may shift the paradigm of research, standardization, and implementation in the field of millimeter wave communications. Introduction. In the near future, the 5G fifth generation system is expected to deliver massively increased channel capacity and data rates. To achieve this, two key technologies have attracted lots of attention recently. The first one is use of a very high frequency spectrum in the range of 30 GHz to 300 GHz, which is also known as the millimeter wave spectrum. The second one is the massive multiple input, multiple output technology, which advocates the use of a large number of antennas in wireless communications. The above two technologies are compatible with each other. In more detail, a short wavelength and millimeter wave helps to minimize the inter-element spacing of millimeter MIMO technology, multiple input, multiple output system. As a result, a great number of antennas can be equipped on mobile devices, which is not practical for the current wireless system that usually works in the sub-6 GHz spectrum. For a given number of transmitter and receiver antennas, the common understanding is that multiple input, multiple output capacity is not frequency selective. If the received signal strength is fixed to a certain level, such conclusion has been validated in the sub-6 GHz spectrum. But this conclusion still holds when we march into the millimeter wave spectrum in 5G. Note that the millimeter wave communication for cellular networks poses its own challenges, such as high free space path loss, high Doppler shift, and blockage. First, other than above factors, and according to more fundamental physics theories, another key difference between the existing wireless communication in sub-6 GHz frequencies and the future one in millimeter wave is the reaction of atmosphere molecules, which can absorb signal energy if excited in the natural renaissance frequencies. Such natural renaissance frequencies are usually in millimeter wave spectrum. For example, if we consider normal atmosphere, oxygen and or water molecules will play a major role in the molecular absorption, and their natural renaissance frequencies are around 60 GHz 120 GHz, 180 GHz. Interestingly, resonating oxygen and water molecules not only absorb signal energy cause attention, they also radiate some of the absorbed energy. This type of molecule induced radiation is often referred to as molecular noises. 2-3, but it is actually highly correlated to the signal waveform due to its radiation nature, and hence it can be considered as a distorted copy of the signal from a virtual non-line of sight path. The aim of this paper is to show how this molecular radiation can change the MIMO capacity performance, as it is very similar scattering, which is known as a very important factor to provide spatial diversity for MIMO channels. Since the molecular absorption intensity is related to the natural renaissance frequencies of the existing molecules in the realistic atmosphere on Earth, i.e., for example, mainly the large amount of oxygen and the water molecules, the energy absorption and the radiation are not flat, especially in the millimeter wave spectrum. Thus, we propose a conjecture that MIMO capacity should vary with frequency due to the impact of such molecular absorption and then radiation. Then we verify our conjecture via theoretical studies and computer simulations, and find that the MIMO capacity increased dramatically in some high absorption band around the 60 GHz, 20 GHz, and then 80 GHz. 180 GHz, thanks to the ubiquitous existence of oxygen and water molecules. The institution of theoretical discovery is that the molecular radiation is a random page onto distortion copy of signal, which equivalent creates a richer scattering environment that improves the line of sight. LOS MIMO capacity commonly evaluated in the millimeter wave spectrum. The impact of our new discovery is significant, which fundamentally changes our understanding on the relationship between the MIMO capacity and the frequency spectrum. In particular, our results predict that several millimeter wave bands can serve as variable spectrum window for the high efficiency MIMO multiple input, multiple output communications, which in turn may shift the paradigm of research, standardization, and the implementation in the field of millimeter wave communications. The rest of the paper is structured as follows. In section 2, we present the molecular absorption model for the calculation of the attenuation and the irradiation, as well as the fundamental theory on the MIMO capacity. Section 3 analyzes the MIMO capacity versus the molecular irradiation, followed by simulation resulted and then insightful discussion in section 3. Finally, we concluded the paper in model 5, channel model and the MIMO capacity. The model absorption model defines how different species of molecules in the communication channel absorb energy from the electromagnetic signals and how they irradiate them back to the environment. This section first explains the concept of absorption coefficient used to characterize the absorption capacity of given molecule species, followed by the attenuation and the radiation models that are built upon this coefficient. Molecular absorption coefficients, the efficient of the given molecule denoted by SI on the radio signal is characterized by the molecular absorption coefficient Ki at frequency f. Such coefficient varies with pressure and then temperature on the environment. The molecular absorption coefficient of many chemical species for different pressure and then temperature are available from the publicity available database such as Heatran 5 and then NIST this atomic spectra. Nevertheless, the atomic air is a mixture of the different molecules, species, and many changes on an hourly basis. 7. Therefore, different climate conditions also lead to different absorption in millimeter wave, and then they should be taken into account when considering millimeter wave channels. In order to model molecular absorption, let us assume the millimeter wave radio channel is medium consisting of n chemical species. M is a mole fraction per volume. For example, the mixing ratio of molecule Si in the channel medium. The further assume that temperature and the pressure of the medium are T and P respectively. The medium absorption coefficient I, for example Kf, and frequently F, is therefore a weighted sum of the molecular absorption coefficient in the medium A, which can be formulated where Ki is the molecular absorption coefficient of species Si on condition of temperature T and pressure P. As discussed before, Ki can be obtained from Heatran 5 and NIST 6. In this work, to get values of Kf, we will use some predefined standard atmosphere conditions and their corresponding ratio of molecules in the air, which are tabulated in 5. Attenuation of radio signal. The attenuation of the radio signal at the millimeter wave frequencies due to spreading and molecular absorption. 9. The total attenuation at frequency f and distance d from the radio transmitter can be written as AF, T, A spread F, T, ABS F, T, where A spread F, T, and then ABS F, D are respectively then attenuation due to spreading and attenuation caused by the molecular absorption at frequency f. In more detail, the spreading attenuation is given by A spread Fd C per A pi Fd square, where C is speed of light. The attenuation due to molecular absorption is characterized as 9. ABS Fd E Kf times d. Main linear approximation for 2 have been proposed in the literature for different frequencies in dB or dB kilometers 10. The ITU radio communication sector (ITUR) also provides various procedures to estimate the specific attenuation due to the dominant molecules in the air. For example, oxygen and water. 11, both of which can be derived from 3 and 4. Thus, the line of sight arrow as received power at the receiver becomes molecular irradiation. The existing molecules in communication medium will be excited by the electromagnetic waves at the specific frequencies. The excitement is temporary, and the vibrational rotational energy level of molecules will come back to a steady state, and the absorbed energy will be radiated in some frequency. These radiated waves are usually considered as noise in the lecture. For example, the molecules absorption noise has been studied in the literature since 1986, when a model for sky atmospheric noise for frequencies higher than 80 GHz was proposed in 3. There are a number of works that have studied atmospheric noise for millimeter waves frequencies, such as 12, which experimentally measured the atmospheric noise variation in Mauna Kea in Hawaii over many nights and days using 143 GHz, 268 GHz transmitter. Recently, the molecular noise has been reconsidered for higher frequencies, such as terahertz band ranging from 0.1 to 10 terahertz. Mercury absorption is in white, and then its power spectral density PSD is not flat because of the different resonant frequencies of various species of molecules. The PSD of the molecular absorption noise that affect the transmission of a signal. SMBS is contributed by the atmospheric noise SMB and the self-induced noise SMB. Xn as addressed in 3.3,A. Where Kf is the absorption coefficient of the medium at frequency, Ft0 is the reference temperature, 296 kb is the Boltzmann constant, Pt is the power spectral density of the transmitted signal, and c is the speed of light. The first term in 6, which is called sky noise, and defined in 7th. In the independent of the signal wave. However, the self-induced noise in 8 is highly correlated with the signal wave 4 and can be considered as a distorted copy of the signal wave 13. Thus, the received power of the irradiated signal by molecules at the receiver can be expressed by PRAFD PTF 1 minus E minus KFD per 4 pi FD per C. Since the phase of the irradiation wave depends on the phase of molecule variation, which varies from molecules to molecules, 14. The received power in the case is affected by the large number of phase-independent irradiated photons. Thus, we assume a uniformly distributed random phase, beta random, for the received signal with its power given by 9. Channel transfer function. The channel transfer function for a signal loss channel is given by H loss FD equal 4 pi FD per C square E minus K FD times EJ E pi 2 pi lambda D. Then the partial channel transfer function resulted from the molecular absorption, and excluding the loss component can be represented by hence. The total channel transfer function is a subposition of the partial channel transfer functions, which is written as MIMO channel model and capacity. In this paper, we consider MIMO system that is consisted of anti-transmitting antennas and NR receiving ones. The received signal vector Y and NR receiving antennas can be formulated as 15. Y equal Hx plus N, where X is transmitted signal vector from the NT transmitting antennas, and N is the NR times 1 vector with 0 mean independent noises with the variance sigma scale. The channel matrix H defined by like this, where Hij is a complex value denoting the transfer coefficients associated with the J's transmitter antenna and the I's receiver antenna. Note that Hij can be obtained from 12 for frequency f and distances at Dij a 3 times 3 MIMO system with the channel matrix is illustrated in figure 1. Figure 1, a 3 times 3 MIMO system, the channel gains of arrays pairs between transmitter and receivers. In this paper, we assume that the transmitter has no channel state information, CSI, and the transmitting power is equally distributed among transmitted antennas. Consequently, the capacity of MIMO channel can be written as C equal log 2 determination I and R plus NT sigma 제곱 scale HH plus, where P is the total transmitting power and I is identity matrix. Since the determinant of I, NR, and T sigma square P HH can be computed by the product of the A values of the matrix HH. MIMO capacity can thus be written in the form of a product of non-zero A values as 16, where lambda I denoted singular values of the matrix H, and hence the squared singular values lambda I square denoted the A values of the matrix HH. Note that K denoted the number of non-zero lambda I square, which is also called the rank of H, with K mean NR and T. 16. Analysis of the MIMO multiple input multiple out capacity with molecular absorption. It is well known that maximum achievable capacity of MIMO channel is proportional to the minimum number of antenna elements at the receiver and the transmitter. However, in an environment that is root of spatial diversity, such capacity would be degraded due to the deficiency of parallel information paths. For example, the rank of the MIMO channel between the receiver and the transmitter. 17. More specifically, is a rich scattering environment. Scatterer provides sufficient and loss signal component, leading to a better diversity and capacity. But in this case of loss scenario, and loss signal component will dominate the received signal, and thus decrease the channel length due to the linear dependence of the loss antenna array phase. Thus, in loss scenario that assume for most millimeter wave communications, the maximum multiple input multiple output capacity is achievable only with some specific array configuration. 18. Where the loss arrays are perfectly orthogonal, result in an opportunistically full length of multiple input multiple output channel. However, this is not practical for mobile communications, since such kind of optimal antenna setting requires a user steadily holding a device toward a specific direction. Generally, the multiple input multiple output capacity becomes higher if the channel transfer matrix H is full rank and then well conditioned. In more detail, the rank of H determines how many data streams can be multiplexed over the channel, and H is well conditioned if the condition is a number which is defined as lambda mean lambda max is small and close to 1. In other words, the maximum multiple input multiple output capacity can be attained when all lambda I are equal. With absorption radiation, we can show that it helps to provide equivalent LOS passes for the LOS scenario, and thus increase the rank and decrease the conditional number of multiple input multiple output channels due to the page limit. We will relegate the full analysis to the journal version of our work. Here we focus on 2 times 2 multiple input multiple output channel as toy example, and prog 12 into 15, which yield 17 show on the top of the next page. In 17 is normalization factor of H, and beta and Nij is the random phases of radiation signal. To show the impact of absorption coefficient on 17 and then MIMO capacity, the channel transfer function and then singular value are calculated for practical range of absorption. Figure 2. Singular value and then condition number is affected by molecular absorption. Higher absorption leading to 2 times more capacity in compared with SISO. coefficient in normal air condition 60 GHz, while the channel distance 50 millimeters and arrays are parallel formation. It should be denoted that the actual value of absorption coefficient at 60 GHz around 2.7 10-2 in figure 2. We plot the result in terms of the singular value and the condition number. As one can observe, for a small absorption coefficient, the largest singular value is much larger than the minimum one. Leading to an air conditions multiple input multiple output channel in matrix. However, as the absorption coefficient increase, the signal values are getting closer, and the inverse condition number of increases from 0 to 1 toward 1, which implies a higher multiplexing gain. Also, it can be seen from figure 2 that the 2x2 multiple input multiple output capacity doubles that of a single input single output channel for a very large absorption coefficient. In the next section, more results for the millimeter wave spectrum with realistic absorption coefficient will be presented. To evaluate the multiple input multiple output capacity in millimeter wave and show the performance impact the molecular absorption, we consider a simple n by n multiple output system with a uniform linear arrays ULAs, where the inter-element spacing is equal to half of the wavelengths at both transmitter and the receiver, and the channel distance is d. The considered multiple output system is illustrated in figure 3. Moreover, we consider uniform power allocation to transmitter arrays operating in one open spaces LOS scenarios. The default value of the parameters are listed in table 1, and different values will be explained when necessary. In order to investigate the multiple output performances, we evaluate the theoretical multiple output capacity with the several configurations. In the first step, the parameters in table 1 are used. More specifically, the channel transmit matrix in 14 is obtained from 12, while the distance between each pair of transmitter receiver antenna element is calculated by channel geometry. Finally, we compute the multiple input multiple output capacity using 16. Since we apply random phases on an LOS component created by the molecular radiation, we conduct the evaluation of the multiple input multiple output capacity with the molecular radiation for 5,000 times and show the average result. We use online browsing and plotting tools, which is based on HITRA databases, to generate absorption coefficient for different single gas or some predefined standard gas mixture of atmosphere at sea level. As shown in table 2, since the oxygen and water molecules play main roles in normal air environment and millimeter wave band and the oxygen ratio environment, we use the highest and lowest water ratio in table 2. For example, the USA model high latitude winter and the USA model tropics. The corresponding absorption coefficient in millimeter wave band have been shown in figure 4 for an ambient temperature is 273 and a sea level pressure of 1 atm. It can be seen that there are three major absorption spikes in the millimeter wave spectrum as follows. The absorption coefficients in two different atmospheres. The temperature is 273 and the pressure is 1 atm. A pair of them appear at around 60 GHz and then 120 GHz, which are attributed to oxygen molecules. Note that the absorption coefficient are the same both atmosphere cases. For example, USA model high latitude winter and the USA model tropics. This because the percentage of oxygen is comparable for those two cases. The third one is 180 GHz created by the water H2O molecules in the air. For a tropic atmosphere, the water ratio is higher than that of the winter atmosphere, and thus we can see significant increase in terms of the absorption coefficient among these two atmosphere cases. For comparison, we also investigate hypothetical vacuum cases without absorption. For example, we set the absorption coefficient is 0. The MIMO capacity vs absorption coefficients. In the subsection, we first assume a constant reflection SNR over the entire frequency spectrum and display the MIMO capacity in bit second hertz for the millimeter wave bands for the 3.3 MIMO with the parallel ULA. In figure 5, in this figure, we MIMO capacity with absorption in compared with absorption. As one observed, the capacity of the latter case flat over the entire band and then not frequency selective, which corroborate and the common understanding up to now. However, when the observer kicks in, significant increase show up in certain frequency band with high absorption. For example, the capacity boosted by around 70% at 60 GHz for both atmosphere case. Furthermore, since the tropic atmosphere contains more water molecules, it reaches considerable capacity increase the 180 GHz in tropic atmosphere in comparison with the winter atmosphere and hypothetical vacuum cases without absorption. The confidence interval of 90% also has been shown in capacity graph figure 5 in order to show the result distribution. Numerically speaking, we can calculate the capacity for SISO channels, which turns out to be 6.66 bit second hertz. According to the existing MIMO theory, for full-length 3.3 MIMO channel with each enough spatial diversity, the theoretical capacity will be increased to 3.666 20 bit second hertz. As discussed before, the lost MIMO channel suffers from poor spatial diversity and can achieve the maximum capacity only with some specific geometry configuration 18, which is not feasible for mobile communications. Thus, it can be seen the MIMO capacity without absorption is close to that of SISO channels. However, if the molecular radiation is taken into account, it can equivalent create a rich scattering environment and in turn increases the spatial diversity and the MIMO capacity as shown in figure 5. Note that in figure 5, we assume a constant reception SNR. However, the actual attenuation varies with the frequency because 1. The free space path loss increases with the frequency, and 2. The molecular absorption also attenuates the signal. Hence, it is interesting to investigate whether the absorption attenuation will mitigate the MIMO performance improvement in high absorption frequency band. For this purpose, a constant transmit power of 1 watt and then constant noise power of minus 100 dBm decibel are chosen in our next simulation. Note that the parameter setting provides SNR value similar to that was used in the previous step. The results are exhibited in figure 6, where the other parameter values are the same as those in figure 5. As one can observe, the absorption attenuation has a marginal impact on the MIMO capacity improvement discussed before. To show this, we also simulate SIS of channel and plot its capacity in figure 6, where we can see that the capacity slightly degraded at high absorption frequency band at ground 60 GHz and 180 GHz. In summary, the millimeter wave MIMO system can take the advantage of molecular absorption and radiation generate more capacity, which prevents absorption attenuation. C. The MIMO capacity and versus the antenna number. The discussed before. 1. The key benefit the millimeter wave communication is potential incorporation with a massive multiple input multiple output technology. Generate a tremendous multiple input multiple output capacity. Hence, in the subsection, we investigate the molecular absorption effect on the multiple input multiple output capacity for our large number of antennas. Figure 7 displays the multiple input multiple output capacities as a number of antennas in both receiver transmitter increases, or the multiple output capacity increases linear as antenna number of increases. Simulators parameter values are based on table 1, except the array angles. For example, theta and pi, which are chosen randomly. Our simulation is repeated 5,000 times, and the average results have been shown in 50, 55, 60, 65, 60, 70 GHz. As can be seen from figure 7, with molecular absorption, the multiple input multiple output capacity increases linearly as the number of antennas increases. Such performance gain is much more obvious for 50 to 65 GHz around the natural renaissance frequency of oxygen, which create an opportunistic spectral window for high efficiency multiple input multiple output communications in millimeter wave. Also note that without molecular absorption, the multiple input multiple output capacity is frequency non-selective and does not increase with the number of antennas due to the dominant LOS transmissions. Such contrast comparison can be easily seen from figure 7. In this paper, we investigate the multiple input multiple output capacity for millimeter wave, where the gas molecules in our atmosphere like oxygen and water not only can increase the path loss, but also can irradiate a copy of signal wave and equivalently create multiple path channels. Our results show that in certain frequency band where the absorption coefficient is significantly high, the multiple input multiple output channels can achieve a capacity that is close to the theoretical limit. Thanks to the great improvement in spatial diversity, our new discovery fundamentals changes our understanding on the relationship between the multiple input multiple output capacity and the frequency spectrum, especially for millimeter wave communications with massive multiple input multiple output.